Especially let's recall what we have seen in the two-dimensional coordinate system. So in 2D, we have two axes, and they are perpendicular, and usually you see the horizontal axis to be the x-axis, the vertical axis to be the y-axis. And let's say if you have a point, move this horizontal axis a little bit lower. So let's say you have a point at 4, 3. As a coordinate pair, right? So you have 4 as the first component, 3 as a second component. So if you just enter our classroom, the QR code on the upper right corner is the attendance QR code that you can scan through your phone. And if you have any issues, just let me know after class. So now, the 4, what does that mean? Basically, it just means if this dot in black, if you do the projection, looks like I erased it. So if you do the orthogonal projection down, perpendicular to the x-axis, it will be the location that's actually a 4 on the right of the region. Right? And then similarly, if you do the orthogonal projection down to the y-axis, that's going to give you a location that's a 3, which is calculated. This is a 3 units above the y-axis. Right? And now you see, okay, the dashed lines and the axis will form you a rectangle. Okay, that's the XY plane that we have seen in the two-dimensional coordinate system. Right? Let me hide the QR code, and let's show this video right now. So this is not really the only coordinate system that you can see in 2D. So think about this. So basically, if you do a rotation of this axis of this two axes, right? So here, what you can see is that the y-axis is always like counterclockwise rotation from the x-axis by 90 degrees, right? So it's just counterclockwise. But now, if you do this rotation clockwise, that's something different. So you may have a horizontal axis to be y, but the vertical axis to be x. Okay, so this is a completely different coordinate system in the sense that you cannot really rotate the black one and obtain the red one on the right. Right? So the only way that you can do it is that you somehow you come out of the two-dimensional plane that you see in front of you. You somehow flip it, okay? So that will give you this kind of correspondence. But within the rotation, within this two-dimensional plane, through rotation only, you cannot really get one from another. So as a remark, the above two coordinate systems are different in the 2D plane because we cannot rotate and obtain one another. Right? Right. So that's pretty straightforward. That this is just 2D. Right? So now what happens in 3D? The three-dimensional coordinate system is going to be 3 axes. Right? Basically, let's draw one. that you probably have seen also. So basically, we will have x, y, and z axis. So this is the layout. So basically, you have x, y. So basically, this is the x, y plane at the bottom. Okay, and then this the third axis that's going to be a z axis, right? Somehow, I would like to mention that in this course, we're gonna draw actually draw by hand a bunch of figures, and definitely a sort of imagination of the 3D figures is gonna be highly recommended. Okay, so it's kind of important. So here, you can think about this as the XY plane as this is a horizontal plane at the bottom. Okay, so or another way to see it is that okay, you can just think about the YZ plane right here as the screen in front of you. Okay, so that's a plane. But then this x-axis just goes from that plane and just point at yourself. Okay, so that's kind of a two-dimensional figure about a three-dimensional structure. Okay. So sometimes, yeah, so that's just like a sketch. Sometimes they would indicate this x-axis direction like this kind of symbol, just saying, okay, this is like an arrow pointing towards yourself. But of course, that's not really easy to illustrate a three-dimensional figure. So that's just about an idea of the direction. But that's the way you can somehow imagine this. Okay. And now, like we have seen before about rotation, right? So of course you can get some kind of different copy of axis just by rotating this system on the left. So let's say, actually, I claim that I can get this coordinate system by simply rotating what you have on the left. They are equivalent. Well, probably you can imagine about the rotation that you can perform, but there's another way to tell that they are equivalent. That's actually called the right-handed rule. So basically, these two systems will follow the right-hand rule that I'm going to introduce right now. So basically, here's the thing. Okay, so let's pull out our right hand. So we have 4 fingers let's try to follow that along the axis direction. Okay, so I'm gonna stand right here. So that's the x-axis direction. So that's the 4 fingers of myself. All right. And now for y, so the y-axis is the direction that you can bend the 4 fingers of yours. Right. So here, this x is pointing towards yourself, and you can bend to my left. Right. So that's the y direction. And now the thumb is now pointing towards the z direction. Okay. So this is exactly the right hand that you can use to somehow follow the directions of the coordinate system. And here is actually the same thing. So now let's look at this one. Okay, my 4 fingers will point towards the right, and then I can bend along the y direction, which is pointing upwards. And now that thumb is pointing towards yourself, and that's exactly the z-axis direction. Okay. Does that make sense? So this one is also following the right-hand rule. Okay. Any questions? So basically, always just remember, a right-handed coordinate system is a system where the x-axis goes through your 4 fingers, and the y-axis the direction that you can bend, and then finally the z-axis has to follow your thumb direction, the direction of your thumb. Okay. That's a right-handed system. Okay. And of course, now, so you can always just rotate your hand in 3D. So that's why you can obtain one from another by rotation. But of course, let's put another one that cannot be rotated from the above in red. So this one, if you have y-axis here, x-axis here, and z-axis here, this is actually a left-handed system. Because let's try this. So now let's follow the right-hand rule again, and let's see if we can get this axis system. So now the four fingers will go along the axis x-axis direction, right? And now I want to bend my fingers along the y direction, which is pointing towards myself. Right? And finally, I see okay, the thumb is pointing downwards. Okay, so if it were a right-handed system, then the axis must be downwards, but now this is pointing upwards. Okay, so this is exactly opposite. Okay? So that's actually a left-handed rule. Okay, so this tells you, okay, of course, you cannot really rotate your right hand and get your left hand in the three-dimensional space, right? So through rotation, you cannot really get one from another. You cannot really get the red coordinate system from the black one, and vice versa. Okay. So that's good. So we have two kinds of coordinate systems in 3D as well. So that's really up to the direction of the z-axis, right? So you have an xy plane, and z-axis could point, let's say from the figure above, right here. So z-axis could point upwards or downwards, right? So that's the only two possibilities of a axis that's perpendicular to a plane. Right? So you have two kinds. Okay. All right. So actually, this is the first important concept from our Calc III course. Okay. All right, now notations and terms. Notations and terms. So usually we would notate the three-dimensional space as R3. So basically, if you recall this R is indicating the real line, right? The set of real numbers. And now we have 3 as kind of like the exponent, but it just says, okay, this is actually a tuple. Okay, this is 3 R's multiplied together. So this is the notation that's just commonly used. But this is so the left hand this left hand side, this is actually a shorthand of this expression in the middle. Okay, but what does it mean? It just means okay, it's going to be the set of all the tuples such that the x, y, and z they are just free real numbers. X, y, z are all real numbers. Okay. So here, this symbol right here looks like an E. This just means belongs to. And the R here, this is the typical notation for that set of all real numbers. So basically, when you talk about three-dimensional space, this is just the set of all tuples that the coordinates are free in the set of reals. All right. Now, so you can see, okay, this is just a direct extension, right? So in 2D we have a pair, right? In 3D we have a ordered pair of 3 terms of 3 coordinates, right? Now, in the xy plane we have x-axis, y-axis, right? So they are coordinate axes. Okay? Here in 3D, we also have X, Y, and Z axes. Okay? But now there's also the idea, the concept of coordinate planes. Okay? So let's say for the XY plane, that's actually the one that looks horizontal to yourself. Okay? So this is the XY plane. And of course, there are two other ones. So we have YZ plane. Right here. Okay. And finally, we have XZ plane. Okay. So now, for some other descriptions, so let's say for 2D, recall that there's a term called the first quadrant. So that's exactly, so this region right here. Which is the region that's above the x-axis and on the right of the y-axis. Okay. Right here. So here, x is positive and y is positive. Okay. So two axes separates the plane, the four regions. Okay, the first one is the one with x and y being positive. But now what happens in 3D? So in 3D, we have three planes, right? So that's gonna be 8 regions, but if we look at it first, that's similar. So we look at the region that x, y, and z are all positive. So that's actually this piece. So I'm just gonna draw a hyperrectangle that's indicating that for whatever point within this region, we are looking at this kind of point, which has x, y, and z coordinates to be always positive. And this region is indicated as the first octet. So here, although we have drawn a rectangle, but essentially we want to express this concept that for the first octet, this is actually the entire region that's in the front of the YZ plane, on the right of the XZ plane, and above the XY plane. Okay? So that's actually an unbounded region all the way in this direction. Let me write that down. So it's actually an unbounded region. Unbounded region. Kind of like infinite cube. And of course, there will be other options, but now we usually just care about the first. All right. Now, let's talk about the pairs. So at the beginning, we have the XY axis and we have a point 4, 3, right? So basically, we mentioned that this the orthogonal projection here will give you 4 units on the right of your region. This projection gives you 3 units above the region. Okay. So this first component, well, this first coordinate in the pair is called the x coordinate. And this coordinate is called the y coordinate. The second coordinate is called the y coordinate. Yeah, I should make this a little lower so it can be part to 3D case. All right, now 3D, we just had one more coordinate, right? So let's say in the okay, let's look at point 111. So let me move a little bit upwards. So I just want to illustrate, let's say this point is 111, then I have to draw some kind of a cube, right? But then I need to give you guys a visual. So what I'm gonna do in a minute is that the red edges are gonna be solid, but the black ones, they're actually on the rear side. So I'm gonna illustrate them as dashed lines. That's the thing I'm gonna do. So they're in the same color. So to illustrate the point 111, actually it's gonna be a cube. But then the rear vertical is the z-axis. And the rear, well, the bottom plane is actually the xy plane. Okay, so to somehow illustrate the three-dimensional relationship, I'm gonna do this. Okay, so dashed are actually the rear edges. Okay, so this is the point 111. And we name this P. Okay, so basically, we have three coordinates, right? So the first one and the second one, they are just the xy coordinates. Like what you have seen in 2D. But then, so the last coordinate 1 is actually about the height. Okay, so that's actually about how much above the xy plane that you're at. Okay, so if you think about this projection method, then from the point you can do the orthogonal projection down to the xy plane. That's actually right here. Okay, so this is actually the orthogonal projection down to the xy plane. So if you do the projection, so basically starting from this point, okay, if you drop it down, then you'll hit the point 110. So that's not gonna be a height anymore. Okay, and this vertical bar has a length of 1, which is exactly the same length as the dashed line, the vertical dashed line at the back. Okay, so that's 1. So that's the 1 here. So why not? Why not I change the color to purple? So okay, this is the 1, but then this tells you, okay, this is actually the height 1 right here. And this also tells you this is the 1 right here. And that's the same thing as this. Okay, so that's the height. Okay. And of course, the x value 1 is just gonna be this one right here. Yeah, let me keep it as black. So this is 1. And that's actually what the edge along the x-axis, right? That's 1 in black. Let me also switch the y as 1, which is in red. Okay. So now what y is actually this one, or it's gonna be this one. It's horizontal along the y direction. And then there's also this one here. The black one is also here, just along the x direction. It's not so easy to draw that bracket. Okay, so this is actually the three-dimensional relationship. Okay, so starting from the point 1, 1, 1, what are these edges? Okay, so the coordinates are all the same, they're all 1, so you essentially end up with a cube. Okay? So now about the terms, so the last entry, the last coordinate is called the z-coordinate, like a direct extension from 2D coordinate. Coordinate. So also I mentioned that 1, 1, 0 is the this is the projection of point P to the xy plane. That's our point 1, 1, 0 right here. So far, any questions? So as a remark, small remark. So 1, 1, 1 actually tells you how to move from the origin to the point P. So the origin is actually the point 0, 0, 0. So basically here, in black, you're just moving along the x-axis direction, right? And then you go 1 unit along the y direction, which is in red, and then you go along the z direction for 1 unit, which is in purple, right? So if you think about it in this way, then actually this is sort of the idea, like a taste of the concept of a vector. Right. Now let's look at another concept, that's the distance. Okay. So in 2D, if you have a point, let's say P right here, and it has 2 coordinates, x1 and y1. So let me just move it a little bit lower, because I still want it to be parallel, just in case you need to keep you need to copy the notes on the upper right corner. And we're gonna keep that as well. Okay, so the point P is let's say this point is the pair x1 y1, right? So this just says the orthogonal projection will be at this location where this is xy units to the right of the region, and here this height is actually y1, right? So this is just y1 units above the x-axis. Okay? And if we care about the distance from the origin to the point P, okay? So you see, okay, this is actually a right triangle. Okay? So the distance is from the origin to the point OP is actually following the Pythagorean theorem, right? That's actually x1 squared plus y1 squared under the bracket. Okay. So the idea here is that you just need to look at the right triangle that you can form within the plane, and that will be it. Just use the Pythagorean theorem. So now, this is the situation where you have only 1 point, right? So let's say if you have another point Q, let's say right here. And let's assume that coordinates are x2, y2. Then if you want to calculate the distance from P to Q, right? So you just need to form the correct right triangle again. So you can see, okay, if this is the triangle, then the horizontal distance, this is gonna be the difference between the x coordinates. And this edge is gonna be represented by the difference between the y coordinates, right? So essentially, the formula is gonna be really similar to the above. It's gonna be x1 minus x2 squared plus y1 minus y2 squared. Call it squared. Okay, so now what happens in 3D? So in 3D, we have one more coordinate. So let's say the point P is the point right here. And we have 3 coordinates, x1, x1, y1, z1. So if you think about the figures that we have drawn a little bit earlier, so let's just quickly take a look. So for a point like this, okay, so this is now the corner of a cube. So here, the point 4, 3 is actually the upper right corner of a square. So that's Pythagorean theorem directly. Right? But for the right, we have a corner right here. So if you think about this, this edge is perpendicular to the xy plane. So if you want to get this distance, this triangle is actually a right triangle. But then this edge is actually, okay, the distance within the 2-dimensional space. So if you follow the Pythagorean theorem, you can actually see that this is the sum of squares. So this square of this and the square of this added up to be this hypotenuse, right? But this will be a side edge of a right triangle. So the true hypotenuse is actually this one. So it's so that's the idea. But then of course we want to draw the figure right beneath this figure. So let's do that. Okay. So that point P is the corner of a rectangle right in front of us. Okay. So in this rectangle, what do we know? We know x1 is this edge, okay, along the x-axis, right? So y1 is this edge along the y direction, and z1 is actually the height, which is yeah, let me think. So let's just stick to the dashed lines because they are all different. Okay. So x1 is this one. So there's no confusion. So x1 is this one. y1 is this one. And z1 is the vertical one. Right? But like we said, if we want to get this distance, it's still a dashed line in red because this distance goes like the diagonal, right, through the rectangle. We form a right triangle through connecting the diagonal at the base. Okay? So we actually know that this is the point P in solid. So x1, y1, z1. And this, let's call it P prime, which is x1, y1, 0. So this is the orthogonal projection down to the xy plane. So the z-axis, the z-coordinate is gone, right? So that's just a 0 there. We actually know that this is right. This is 90 degrees and perpendicular. And what do we know about the bottom dashed line? So from the equation on the left, okay, from this equation, we actually know the length of the dash at the bottom. That's exactly x1 squared plus y1 squared under the bracket, under the square root. Because if you look at the bottom, what do you see? So you have along the x-axis xy units, along the y-axis you have yy units, right? And this diagonal is exactly this, right? So this is all, this is P prime. Okay, so now, so this is the bottom, okay? And now for this dashed line, now it's in solid. So what do we need? We just need the square of this plus the square of this, and then we'll put the whole thing under the square root. That's actually the square root of the square of the bottom plus the square of the height, which is z1. Okay. So this is the hyperrectangle. And looks, yeah, let me move it a little bit to the left. So yeah, a little bit space everywhere. Now, to formally put things down, distance from O to P, okay, equals to the square root of now. So if you think about the if you simplify the radical expression, you see, okay, under the square root we have what? We have x squared, x1 squared plus x2 squared plus under the square root we have what? We have x1 squared plus y1 squared plus z1 squared. So exactly just the coordinates squared. So sometimes when you think and talk, just say something wrong. But exactly these are the components. Okay? These are coordinates squared under the square root. Taking this off. So in a way, this equation is exactly the extension right here. Okay? So basically, you have the z1, you just introduce that under the square root. And similarly, if you have another point Q in the three-dimensional space, let's write down the formula. For P with coordinates x1, y1, z1, and Q with coordinates x2, y2, z2, then you can still think about this as the direct extension from here. Okay. So basically, we have the difference of the x coordinates, difference of the y coordinates, and finally, we just need to introduce the difference in the z coordinates. So the distance from P to Q is just going to be the square root of the 2 points taking the difference in the x coordinates squared, the difference in the y coordinates squared, difference in the z coordinates squared. So, any questions? So the figure right above, following the Pythagorean theorem, that's the derivation, of course, is not that critical, but it just somehow help you visualize what's happening. Okay? But the formula is always not going to be complicated. Just direct extension. Right. Okay, so these are about the distance. Now, the next topic. What happens if you have a fixed distance from the origin? So in 2D, it's actually a circle, right? So if you have xy plane, and then let's say if you have x squared plus y squared equals 1, so that's just saying, okay, the point xy has a fixed distance to the origin, which is 1, right? Which is a circle. So this is going to be an intercept -1, 1 on the x-axis, and this is going to be the intercepts of -1 and 1 on the y-axis as well. So we know this is a circle. We know the distance from any point on the circle to the origin is 1, because you can always just write this sum of squares under the radical, right? So if x squared plus y squared is 1, then the square root of that is also 1. Right? So here, this is the let me put down here the set of all points whose distance to the origin is all 1, right? So basically, if you want to just illustrate the set of all points whose distance to the origin is 1, that's gonna form you the circle. Okay, so there's a question. What was there a QR code for the attendance? Oh, Jason, the QR code is for the in-person class. It will not be displayed on Zoom, but closed caption. That's for this. Okay. Yeah, so that actually. All right. Any other question? All right. So what happens in 3D? So in 3D, if you have x squared plus y squared plus z squared equals 1, you can expect that's a sphere. Okay, so it's actually a ball, the surface of a ball. So like this is kind of a common sense, right? So basically, on a sphere, all the points are having the same distance to the origin, to the center of the sphere. Right? So if you have x squared plus y squared plus z squared equals 1, they're just saying, okay, the square root of the sum of squares equals 1. So that just says, okay, the distance from whatever point on the sphere to the center, to the origin is 1. Right? Y-axis. So as you can recognize that the coordinate systems I'm doing is always the right-handed. Right? So exactly you have xy axis on the horizontal base, and z is the vertical axis going up. Okay. So this is a sphere, and the radius here is what? Okay, so this quadratic equation gives you a circle on the left, a sphere on the right, right? What happens with the linear equation? So let's say if you have y equal to 5, actually this forms your a line, right? In 2D. So y equal to 5, this means okay, the y coordinate is always a constant. So this is at the point 0, 5, that's actually on the y-axis, and that's of course on the line. But of course, whatever point that's having the same y coordinate is also on the on this line, line. Okay, so now if that's a line, then what happens if you are in 3D? What do you think? The same equation, y equal to 5. What does it give you? So now y equal to 5, right? So that means okay, x and z coordinates are all free, right? So originally we only have x to be free, but that's one dimension. So now you have x and z to be free. That means it's two-dimensional, right? So it's gonna be actually gonna be what? Anyone know? Anyone have to guess? Like plane, right? So basically, here, if you think about the plane, it's actually the plane that the z value is always a 5. Okay? So on the y-axis is so on the y-axis you have the same intercept. Should dash right here. Now here, although I have drawn a rectangle in a way, but this is the idea is that this is definitely going to be an infinite thing because this is a plane. We don't really have a boundary. But as an illustration, a plane is just going to be something like this. Before I let you guys go, the final remark. An equation of a sphere with center, let's say cap C, with coordinates h, k, and l, and radius little r is the following. So basically, just following the distance equation. So x minus h squared plus y minus k squared plus z minus l squared is going to be r squared. Okay. Right. So as a remark, three an equation involving x, y, and z presents a surface so just like what we see as the plane y.5 or the sphere equation, right? So that's the sphere equation is an example of the surface 3D, which is really different from two-dimensional case. Right? So recall. If you have one equation, then it will define your curve, right? In 2D, in the xy plane. So in 3D, we have two questions as follows. Question one is x squared plus y squared plus z squared a surface? Two is a combination of two equations, namely x squared plus y squared equals 1 and equals 3. Stop video. A surface. So, just now we were saying, okay, if we have one equation, right, then it's a surface. But in question one, we only have the expression, it's not really the equation. So answer. X squared plus y squared plus z squared equals 1 is a sphere. Which is centered at the origin, right? And the radius is 1. Which is a surface described in one equation. In particular, the equation describes set of all points x, y, z in the three-dimensional space that satisfies this equation. And it is a sphere. However, so basically the distinction is that for an equation, it will define you some relationship in the three-dimensional space. Right? But if there's no equal sign, the expression only is the sum of the components squared is not an equation. So it is not a surface. So, well, if you think about it, in a way, it's a kind of a functional expression, right? So basically, for x, y, z values that you somehow specify, then this sum of squares just calculates you output. Okay? So there's a polynomial. So if you think about what you have seen in 2D, It's really similar. So let's say if you give the equation y equals x, this is actually a line, right? So whatever equation in 2D will define you sort of a curve. And if you have y equals x in the xy plane, then that's exactly this line going through your region with a slope of 1, right? But then if you only put x or something like x cubed or like x squared plus 1, it's not a line or a curve. You somehow need to give an equation to define this relationship in 2D. So that's the point. Right, so that answers my question 1, right? So now question 2, we have now 2 equations. What does that define? For x squared plus y squared equals 1, and at the same time, z equals 3 in 3D. So this is actually not so difficult to sketch. If you think about it, x squared plus y squared is actually equals 1, so that's actually like a circle in the xy plane, right? But now we're saying, okay, z value must be 3. So z value is essentially the height of the object in the 3-dimensional space. Right? So firstly, let's sketch the axes. So this is x, y, z. Okay. So if you think about only x squared plus y squared equals 1, that's actually the unit circle in the xy plane, right? So let me just draw it in dashed red. Okay. So this is x squared plus y squared equals 1 on the xy plane. So you notice that xy plane, there's no height, right? So z there is exactly 0. But now we are saying we want to satisfy this x squared plus y squared equals 1, and at the same time z must be 3. So that means the z coordinate is now 3 everywhere. So basically you have a circle that's right above this red dashed circle. And the z coordinate is exactly 3 right here. So every point will have the form x, y, 3 in the last component coordinate. So x squared plus y squared equals 1, that's specifying the xy relationship, right? And then at the same time, you must have z equals 3. So you see, okay, we have a system of 2 equations, and essentially this defines as a curve. And actually later we will see that, okay, x squared plus y squared equals 1, this equation, of course, this is the surface, but what's the surface? This surface is actually a cylinder. Okay, so this is actually kind of a 3-dimensional object that's surrounding the top and bottom circles. Okay. And finally, z equals 3 is actually a horizontal plane. So you have the intersection of 2 surfaces. So here, the point is that this is a system of 2 equations. And we have, in this figure, a curve. Not the surface. Right. So that's about the geometry. The next example, let's look at an equation So we look at the following surface. Described by the equation x squared plus y squared plus z squared minus 2x plus 4y minus 6z equals 39. Right? So this equation defines you some kind of a surface. It's possible that it's valid, but it's also possible that it's degenerate. It means it doesn't give you anything reasonable in the three-dimensional space. So we wonder if this is a sphere or not. If it is a sphere, we want to look for the center of the and the radius. What is the coordinates of its center and its radius? So this is a very important kind of question for this section. Okay, so we recall that the formula of a sphere actually has two important components. It's the center, which is HLK with three coordinates, and then the radius is on the right hand side squared, right? So sphere is described by the formula, which is x minus h squared plus y minus l squared plus z minus k squared, and the square is on the outside of the bracket. So the right hand side r squared is the radius squared of the sphere. Okay. But now, so simply we want to match this form of the equation with the equation that we start with. Okay. So somehow this process is called the summation of squares. So if you are familiar with this, great. If not, then let's just do it. So another way of writing the formula that we are familiar with is that we just multiply things out, right? So we have three squares. So equivalently, these are so x minus h squared is what? Is x squared minus 2xh. Well, let's put the constants in the front. So it's 2hx plus h squared. So this is the first bracket. And then for the second bracket, we also just multiply things out. That's gonna be y squared minus 2ly plus l squared. And the last one is z squared minus 2kz plus k squared. And the right hand side is still the same thing, r squared. Okay. So these two equations actually mean the same thing. They are equivalent just up to the squaring, right? But then we start with something like this. So it's really closer to the second equation that we have. So basically, if you look at the difference, what's only different is that, okay, there are constants h squared, l squared, k squared, and r squared. So these are the constants that are separate on the both sides of the equations. But and the equations that we start with, there's only one constant on the right hand side. So somehow you want to just match. You just want to do some algebra to the top equation, and you get the form of the bottom. Okay. That's the completion of squares that we want. complete the squares. We have the following. So basically, notice for these expressions, they have what? The form is like x squared minus, we have the x portion, but now we have 2hx. So from the equation above, we want to identify what is h, right? So h is the x coordinate of the sphere. And the way we do that is, okay, we see this is negative 2x as the linear expression. So we can identify that h must be 1. And how do we get that? So the constant in front of x is negative 2, right? And if we just compare with this expression right here, so we use that negative 2 in front of x divide by the negative 2 in front of h. We do that division, that's h, which is 1. And let's put that down. So in the equation at the top, we have x squared minus 2x, so we put them together. We have y squared plus 4y, we put them together. And then we have z squared minus 6z, right? So we put the z's together also. Now, for the h part, we do a plus, because this h part we have a plus, right? So now what's h? The negative 2 in front of x, we divide by negative 2 in front of hx, right? So that will give us the h. Plus, now, if for the y portion, 4y, that's linear expression, that 4 we divide by negative 2. So that will give us L. And finally, now we have negative 6z, right? So just matching. So we want to get k. So we expect that this is negative 6 over negative 2. We do the division, that will get us the k. Right. You see, so this is the way that we play with the equation on the top that we start with. We match it with the second equation in the bracket. Right. Yeah, so let me draw some underlines to indicate what we are actually doing to match with the equation right here. Okay. This may help you to see what's going on. Right. So so that's the first step of the completion of squares. Are we clear about this part? Okay, so now I see many of you are nodding. So now what we have done, we just rearrange the order of the expressions in terms of x, y, and z, right? But now we add some squares, right? So at the beginning of the equation, we add things on the left-hand side. So we want to do the same to the right-hand side as well. So this thing equals to 39 plus these squares that we added. So that's what we want to do in order to keep the equation equivalent to what we start with, right? And now we're getting close. So once we have this form, we are able to, so this equation that we have is exactly this type, right? And then we just write the equivalent expression that has squares surrounding x minus h, y minus l, and z minus k. So we just write it as x minus 1 squared. So what's that 1? This 1 is exactly h, which is negative 2 over negative 2 right here. Okay. So that's the division that gives you the h. Then plus. Now, y minus l, right? L is what? L is 4 over -2. So that's minus the -2. So this -2 is 4 over -2 that we have done for the division. Is that clear? All right, finally, for the z part, plus the z minus, okay, we have k. Now k from the division is actually 3, right? So the 3 comes from -6 over -2. And now on the right hand side, we want to also simplify a bit because these are squares and we just want to get a single number. So we have 1 squared, which is 1. We have -2 squared, that's a 4. Plus finally, we have 3 squared, that's a 9. So if you add things up, so that's actually 49 plus 3 is 53. So and if you want to match, here we have r squared on the right hand side and r is the radius. So in this case, we have 53 is not really a complete square, but we can just write it as the square root of 53 whole thing squared. So what's within the square is actually that radius, right? And now, here we are able to conclude what that center is. So the equation of interest is equivalent to the following. So which is x minus 1 squared plus now we see we have y minus -2, which is y plus 2 squared plus z minus 3 squared. Holding on the right hand side equals to the root 53 over whole thing squared. So from this formula, we are able to see, from this equation, we are able to see that thus we have a sphere centered at the point 1, -2, 3 with radius square root of 53. That's good. So if you start with some random equation that the right hand side is not so it's let's say -100 or something, then this thing is -100, then what you add up is a negative number in the front, right? So if that happens, then the right hand side is, while the left hand side is the sum of squares as positive. In that sense, then although you start with an equation, but it's not really defining you anything reasonable. So in that case, although the appearance looks to be a sphere, but the radius is even not unreal, right? Imaginary. So that's something you may see if you only start with some general equation. All right, so now let's move on to the vectors. So that's the key objects that we want to talk about. Vectors. So what are vectors? Vectors are quantities that has both magnitude and direction. Recall, a real number is a quantity that has both absolute value and the sign. Okay. So basically, you can think about a real number on the real line as a vector, as long as you take the distance from the real number to the origin to be the absolute value, and the plus or minus sign to be the direction. Okay. But now the vectors are a little bit more general. Example. So now there are two things, right? The magnitude and direction. Okay. So if we think about it, for whatever a vector, there's always a starting point and there's always an ending point. So let's say this is vector from A to B. So we usually, this is just we have 2 points within the 3-dimensional space, but then there's a head that's at B, and there's a tail at A. So we always draw this as an arrow. Okay. So we can also name this vector as another using another letter. Let's say V here. Okay. So at the top there's an arrow above V that's indicating that this is a vector. And then we can draw another vector that's from C to D, and we can name it as U. Here, the vector U equals to vector V if they have the same magnitude and the direction. So if they have the same direction, that means these two line segments from A to B, from C to D, they're parallel, right? But then when they have the same magnitude, it just means the lenses are the same. So basically, for the vector right here, V, it can be written as from the vector from A to B, right? So here, I just want to mention that A is called the tail and the B is called the head. Right, so now, each vector, there are two important components, magnitude and direction, right? So what happens if you want to add two vectors? So, the first way is that if we have U and B, then we can form a triangle. So let's say this is the vector U. So the tail and the head of U is like this. So for another vector B, we can stack the tail of V at the head of U. Namely, I'm now starting from the head of U, and then we're ending at another point. So this is the vector V. Okay. And now, to do the sum, that's actually the third edge of the triangle. So this is called the triangle rule. Triangle law. So whenever you're adding two vectors, you can stack one of the tails at the head of the other vector, and then just combine the traveling effect in a sense, right? So this is the triangle law. And now what happens if you don't want to stack the head and the tail? So if you put the tails all together at the same place, so this is U, and let's say this is V, right? So if we have this, then what do we do? So this is called the parallelogram law. So basically, what we do is we just establish the parallelogram based on these two edges. So we just draw the dashed line parallel to V, and then we start from the head of V. We draw the parallel line that's parallel to U. Okay. So this will form you the parallelogram. And what do you know? You know, okay. So this vector right here actually is V, right? Because they're parallel, so so this vector and V has the same direction, and the magnitude is of course the same because you have the opposite edges of the parallelogram. So this is V, right? So you can expect that the sum of the vectors U and V is actually the diagonal right here. So this is a parallelogram. This parallelogram law. So if you just keep the tails at the same place, then you just form this parallelogram, right? And you get the diagonal. Right. Sounds good? Okay, now, modification. So if we have a vector V right here, so what happens if we multiply a 2 in the front? So this is really similar to the real numbers. Basically, if you have this vector V, you are specifying the direction, and then if you multiply a 2, let's say, okay, I want the same direction, but I just want to scale. I want to scale the magnitude to be twice of the original, right? So in that sense, you are following you just want to draw a parallel vector that is the same direction, but the magnitude is twice as the original. To be. And if you multiply a half in front of V, that's actually saying, okay, it's the same direction, but the magnitude is 1/2 of the original. Right. And if you multiply -1 in the front, that's saying, okay, so just like 10, you get to -10. This is still on the real line, but it's just the opposite direction. Right? So if you just if we were negative, then you just flip the direction, but it's still the same parallel direction. It's just opposite. Right? So that's pretty intuitive. So now, question: what is the difference between vectors? What is U minus V? So if you think about the difference, you can always think about it as U plus -V, right? So difference of vectors. So let's say, let's try the triangle again. So let's say we have U and V like before, like this. Okay. We have the tail V at the head of U, so stacked together. So now, we want U minus V. So what we can do is we first negate V. Right? So for the negative of V, that's exactly the opposite vector along the same line of V, right? So that's negative. And now, okay, so U and negative V, they have the tail of one stacked at the head of the other, right? So we just do the triangle. That's U plus negative V, right? So that's U minus V. So U minus V is exactly U plus negative, right? And of course, this is a triangle, right? So if you want to do the parallelogram, it's also doable. Let's just copy this part. And if you want to do the parallelogram, what do we know? So we know V is from the left to the right, right? So if you want to do the parallelogram, you want to have the tails stacked together. So firstly, we establish V, which is this one. Okay, from the right to the left. And at the same time, we just establish U from the bottom to the top again. So this is U. And this red one is negative, right? So now they have the same tail. So now we just draw the diagonal, right? So starting from the same tail and the diagonal of the parallelogram is exactly this one. So you see, either way, you will get the same vector in purple. So that's good. Very important. Right. Now, components of vectors. So in 2D, we were talking about points. Let's say if you have a 4, 3, that's actually a point, let's call it A in the XY plane, right? So basically 3 units on the right and, excuse me, 4 units on the right and 3 units above the origin. But now if we get the vector starting from the origin to this point A, so this vector U, we want to give it a little bit different notation. So here, OA, this vector, is the same as the vector U that we just illustrate in the figure. But now we want to keep the coordinates in the angle brackets. Okay. So that's indicating that we have a vector. So the way that's traveled is, of course, still it's travel 3 units on the to the right and 4 units to the right, 3 units above. Okay? So it's still the same coordinates as the point A, right? But the notation is a bit different. That's the only difference. And now if you think about it in 3D, then we know that for a point, it's actually the corner of a rectangle, right? Half a rectangle. So let's say our point P is having the coordinate of, let's just put the point here, P is one half. And then if we write the vector from the origin to that point, that's actually, once again, in angled, brackets, 1.5. But now, in order to sketch it, we need to realize that, okay, so this is the corner of a hyperrectangle. Then like this. Let me move the point a little bit to the right. It's P. And the coordinates. Okay, so this tells you, okay, so one half, right? So this part, the x intercept, I would say, is 1, the y-intercept 1, the z-intercept is 1/2. Okay. So this is just saying, okay, I'm moving 1 unit along the x-axis and 1 unit along the y-axis, and finally 1/2 above. Okay. So this is my vector u. All right. Now, what happens if we have 2 points that are not the origin? So let's say we have the point A right here, which is having which has the coordinates x1, y1, and then I have another point B, which has coordinates x2, y2. Right. And here, OA is this vector, OB is this vector. But let's say we want to get the vector from A to B, right? From the figure, what do we know? From A to B, we have the head is B and the tail is A, right? So if you think about AB, you can think about this as the vector OB minus the vector OA, right? So traveling along the red vector is sort of traveling from O to B, and then just traveling from A to O, right? So actually this is the difference. Right? So AB is exactly OB minus OA. So if you think about it, you can always think about this as head minus tail. The head is B, the tail is A. So it's OB minus OA. So if we do that, then we can write down the coordinates. So OA is the angle brackets in terms of x1, y1. That's the vector from O to A. Similarly, OB is just x2, y2. But now, AB is the head minus tail. Okay, so head is x2, y2 minus x1, y1. That gives us x2 minus x1, y2 minus y1, which is exactly OB minus OA. Okay. So what we do is we just use the first components. We do the subtraction in the order that we want. Right. So now, okay, so that's 2D. So what happens in 3D? It's going to be really similar. So the only difference here is that we have 3 coordinates, right? So let's say we have a point P, which is x1, y1, z1. We have a point Q, which is x2, y2, z2. And then OP is this vector, OP is this vector. And then PQ is this vector. We know that PQ is OQ minus OP. It's the same idea, head minus tail. So OQ minus OP is exactly x2 minus x1 in the x coordinate, and then y2 minus y1. Get a little more space. Z2 minus z1. So the last note before I let you guys go is that, of course, when you flip the direction, then you just flip every entry. So OP minus OQ, this is exactly opposite vector, right? This is TQ. QP. Starting from Q to P, that's exactly the opposite as OQ. I'm sorry. So we are gradually setting things up, but I want to emphasize that in our course, we have a really big emphasis on the geometric perspective of things. So if you only just think about the arithmetic calculations like doing the sum and difference of vectors, that's actually really simple operations. But and of course, if you talk about the distance between points, like the magnitudes of vectors, it's not really complicated. But the geometry is something very important. Because it's 3D, we can always do graphical illustrations, right? So now let's so we have done the difference between vectors, and now let's start with the standard basis. Standard basis vectors. So basically, in 3D, we have let's just call ijk to be the three basis vectors. So I is the vector that has 1 in the first component and zeros everywhere else. J has 1 in the second component and 0 everywhere else. And finally, K is the one that has 1 at the last component and 0 everywhere else. Okay. So if you look at the right-handed coordinate system, x, y, z right here, then I is exactly just going 1 unit along the x direction. J is exactly the vector that's going 1 unit along the y direction, and finally K is just going upwards along the z direction for 1 unit. Okay. And then since we can express yeah, that's 3D. So let me also just point out in 2D, it's just going to be a little bit simpler because there are only 2 axes, right? So we only have I, which is 1, 0, and J is 0, 1, right? So for the standard basis, and you see that in the figure, these 3 vectors are perpendicular to each other, right? And it's also the same thing in 2D. So I and J, they're going to be perpendicular to each other. And then as a fact, every vector can be represented in terms of the standard basis. Okay. So now, for any vector A that has components A1, A2, A3, we can express this vector A as the sum of three vectors in terms of ijk. So it's going to be A1 I plus A2 J plus A3. Okay. Right. Because essentially the idea here is that we are eventually moving along the x direction for A1 units, that's A1 times I, and then A2 is in front of the vector J, right? That's at the second component, and third component is A3. So that's just saying that's the way I'm moving. And of course, if we sketch it in 3D, it's also doable. It's just that we need to be careful when we draw that rectangle, since those axes are going to be dashed lines. So let's say if we want to sketch the vector A equal to 1, 3, 1, let's say. So basically this is saying what? This is saying, okay, I'm going to move along the x direction for 1 unit, and then 3 along the y direction, and 1 along the z direction. Okay. So okay, I'm going to do the dashed lines in red. So basically, I have 1 unit upwards, 1 unit towards myself, but 3 units to the right, okay, along the y direction. So that's 1, that's 1, that's 3. And I'm gonna complete the axes by solid lines in black. X-axis, origin, y-axis, z-axis pointing upwards. Right? Okay, so if you recall, the vector A is actually going to be the diagonal vector that's going from the origin to the corner of the opposite corner of the rectangle, right? But now, somehow to establish, let's say I plus 3j. So this is I, right? So this is 3j. This is 1k. It's just k. Pointing upwards. I want to draw the arrows for the vectors. But then now, I plus 3j is actually the vector in the xy plane. And let me just draw that rectangle. But of course, it's following the parallelogram rule, right? So that's the diagonal vector right here. So this is I plus 3j. Right? And then if we add k, it's going to be, we can just use the triangle law. So I'm going to make a black one upwards for 1 unit. Okay. So essentially, this vector, yeah, this is a bit longer than the one that I want, because I want it to be exactly parallel and have the same length as the dashed one upwards on the left. So this vector the diagonal will be I plus 3j plus k, right? I'm just gonna draw an arrow here. So that is gonna be I plus 3j plus k. Right? And finally, let's complete the diagram. So we have these edges. We have these edges as the top of my rectangle. Right? So that purple vector is the vector A. Okay. So it's the diagonal of that rectangle in front of us. And this one is K. Okay. So it's good. Right. So this is expressing a vector with some arbitrary components in terms of I, J, and K. Okay, in a three-dimensional figure. Right. So here comes one question. Make sure to double check yourself. If A is a vector that has components 1 to -1, and B is another vector that has components 4, 0, 7, express 2A plus 3B in terms of IJK. The center basis. So basically what you do is just multiply the multipliers in front of the vectors, right? So that's component-wise multiplication, because this is scaling, and then every component we just add things up. So you can check that the answer should be 14I plus 4J plus 15K. Make sure to work on that yourself. Video. Now, so we mentioned that the vector has two important components. One is the magnitude, and the other one is the direction, right? So how do we calculate the magnitude? So you notice that the vector is always in the purple form, where we actually pointing from the origin to the location of the head of the vector, right? So that's actually this point is 1, 3, 1. And let's just write it down. Also, this is the destination of the vector, which is the head, and that's actually the point in round brackets 1, 3, 1. Right. And the vector is the vector in purple. That's just indicating this displacement, in a sense. So the magnitude of the vector directly relates to the distance from the origin to the head of the vector. Okay. So magnitude. So for vector A that has components A1, A2, A3, the magnitude denoted by so the notation is exactly the same as the absolute value notation of a real number. You can say this is absolute value, or you can say usually it's going to be called as the norm. Sometimes you can use a double vertical line on both sides instead of single vertical lines. Okay. called the norm. And this is calculated by exactly the magnitude, the distance from the origin to the head of the vector, if you make the origin to be the tail. So the magnitude or the norm of the vector A is the square root of the sum of components squared. So indeed, this is exactly the distance of that vector A, starting at the origin, ending at the points A1, A2, A3. So the norm of the vector A is exactly the length of our line segment from O to P, which is calculated by Pythagorean theorem, right? Okay, so that's the magnitude part. So the calculation is exactly this distance formula. What about the direction? So if we isolate the magnitude and the direction, then in terms of the direction only, we don't really want the magnitude to take into play. Right? So the magnitude of the original vector, let's say this vector, will not really affect the direction that you are pointing at. Right? And in this sense, the direction is always going to be represented by a unit vector. Basically, that's a vector that has the magnitude of unit vectors are vectors with magnitude 1. For example, so the standard basis, they all have magnitude 1, right? I, J, and K, they are unit vectors, right? So for whatever vector that has a magnitude of 1, that's going to be a unit vector. So what do you think? How many unit vectors are there in 3D? Do you have a guess? Pardon? 3. So of course we have the 3 already, right? There could be more, right? So a slightly different direction with the unit length still gives you a unit vector. So I mean, so now we are looking at the vectors with magnitude 1. They just say, okay, if you start from the origin, it will land on the unit sphere, right? And as long as the head is on the unit sphere, we have a unit vector, right? So actually, this is infinitely many of those. So for the unit sphere with the center at the origin, for whatever vector that you draw, where your head is on the sphere, that's gonna be a unit vector. So unit vectors can be used to describe directions. And there are infinitely possible directions within the three-dimensional space, right? For whatever direction you can always just extend the array and intersect with the unit sphere, right? So if the vector A as long as the vector A has non-zero magnitude, then we are able to find the unit vector along that direction. The unit vector that has the same direction as vector A is the following. So A has a magnitude, right? But now we want to keep the same direction, right? But then we just want to make the magnitude to be 1. So what do we do? So we can somehow scale it, right? By dividing by the magnitude of this vector. Right? So you just scale, but here you are just doing the division component wise, right? So, or you can write it as what? You can write it as the vector A, whole thing dividing by this scalar, which is the magnitude of the vector. So if you do this, okay, originally you have the magnitude of A, but now you divide by this number, then you're gonna get the magnitude of 1. Right? You put it down, this is things. Now, if you take the magnitude of this scaled vector, if you go back to look at the calculation formula for the magnitude, you know, yeah, let's quickly take a look. So basically, we're looking at this. We're just saying, okay, every component we divide by a constant. That constant is the magnitude, right? So that's a common factor of the square. But that square, we can take it out of the square root. And once you take that out, that square is going to be gone. So that's exactly why for a positive constant multiplier, we can always take it out. So yeah, let me put it down here. So for whatever t in front of the in front of the vector, we can take it out of the magnitude as long as t, if t is positive. Of course, if it's 0, it's also true. But if it's negative, then we need to flip the sign. Right. So here, 1 over the magnitude is always a positive number, right? So we can take it out. And now within the magnitude, we only have the vector A left there. So now you see, okay, we have the magnitude of A divided by the magnitude of A, right? That's exactly what. Positive scalar. Scalar. But look. Okay, so now geometrically speaking, what does it give you? So for whatever vector A, like this, right? So the unit vector is exactly along this direction, but only has a magnitude of 1. So it could be something like this. It could be this vector, and this vector is expressed by our division right here. So basically, this is vector A dividing by its magnitude. Okay. So along the same direction, let me put it a little bit more solid, so it's exactly the same direction. Remark. So now we have isolated the two components, two important features of the vector, namely the magnitude and the direction. Right? So we can always write this down. Basically, this part is the magnitude, and the rest is the direction, which is a unit vector. right? And this multiplication is exactly, yeah, although that I wrote the dot, but this is just indicating the scalar multiplication in front of the vector. So here, as an we just need to emphasize that vectors are quantities of quantities with magnitude and direction. So the magnitude is by the calculation that we have in the a few while ago, but then this direction is a unit vector along the same direction. Okay. So we mentioned that the unit vector can be calculated as long as we have a non-zero vector. Okay. What happens with the zero vector? So zero vector is exactly the vector that has all components zeros, right? So zero vector is saying, okay, we're not moving anywhere. And then if you think about the magnitude is also zero, right? So it's not really reasonable to define the unit vector along this direction. So zero vector does not really have a direction, because it's not actually going anywhere. Right. Example. So find the magnitude and the unit vector in the direction of the vector 2i minus j minus 2k. So we want to calculate the magnitude and the unit vector along its direction. So the two features, the two important components of the vector are captured. Okay. So we have, so basically we firstly calculate the magnitude and then we do the component-wise division, right? So we have the magnitude of this vector 2i minus j minus 2k. So basically we just take the square root of all the components squared and added up, right? So the first component is a 2 with squares. The second component is -1 with squared. The third component is -2 and with squared. So under the square root we have what? We have 4 plus 1 plus 4. So eventually you will have the square root of 9, which is a 3, right? So fortunately we have a rational magnitude. So the magnitude is 3. So now, so how's it good? So the same formula as the distance formula between 2 points, right? So once again, for a vector, we just have the tail at the origin and head at the point in 3D as having the same coordinate as the vector that we have. Okay. So that formula is exactly reused. Now we just do the scaling. Okay, we divide by the magnitude to get the unit vector. The unit vector along the same direction is the following. So we just use 2i minus j minus 3k to divide by its magnitude. And then we know, okay, it's so the denominator is just a 3, right? So basically every component we divide by 3. So it's going to be 2/3 I minus 1/3 j minus, okay. Oh, wait. I do notice that I'm copying things wrong. So that's a 2. That's a 2. So why is it a 3? So that's a 2. And then that's a 2/3. Was good? So remark. So everything is actually not really complicated so far. So we do realize that we can also just extend it into a higher dimension for everything we have introduced so far. For any dimension, n greater than 1, we can define vectors u in a similar fashion. So notice that in 3D we have a vector of 3 components, right? In 2D we have a vector in 2 components. So in general, if you have n components, let's say 1000, then you just have a vector, a long tuple that has 1000 components. Okay? So basically, of course, we just write it in angle parentheses so that it's we know that it's a vector. So it's u1, u2, all the way up to un. So basically, you just list all the components, right? And then, so the magnitude is exactly following the Pythagorean theorem. So in n-dimensional space, we always have that the axes, the n axes are going to be perpendicular to each other. So the Pythagorean theorem still holds. So it's going to be the components all squared and added up. And then we take the square root. And then if you think about a scaling, let's say if you have a c that's multiplied in front of the vector u, so that's going to be the component-wise scaling. So what you do is you just multiply the same constant in front of each component. So that's really standard, right? And similarly for the sum and difference of vectors, you can also do it component-wise. So u plus v is just going to be component-wise addition between the vectors, and then the difference is also going to be component-wise. But then the geometric perspective is also the same. So if you have the vector u and the vector v, then in the n-dimensional space, it's still going to be the parallelogram rule. Okay, so the diagonal of the parallelogram is going to be the sum of the 2 vectors. And then if you do the difference of 2 vectors, right, then it's going to be the other diagonal. And okay, so here comes my quick question. So for this diagonal and direction, so what do you think? What's the difference here? Is it u minus v or v minus u? U minus v or v minus u? What do you think? Which one? So we have this vector pointing downwards. What do you think? Do I have an answer? Just a guess. I do hear two answers appear. So so if you think about the vector difference, right, it's always the head minus the tail. Okay. So now the head is at v. right? So this vector that we are looking at, the head of this vector is the same as the vector v, right? So it should be v minus u. V minus u. And u minus v is the opposite, right? So why is it v minus u? So if you think about it, basically v minus u is saying we have v, and we go along the negative u direction also. You see, head minus tail. That's very important. All right, so this gives us the end of this long section 13.1 and 13.2.